Oh, I thought of one more thing I should talk about since you're all, well, everyone's almost here. In terms of progress logs, to the best of my knowledge, with a few exceptions of late work, I think I've handed back everything except for the lab that's due today. And I'm going to try to have that back to you tomorrow so you can have that completed. And if anyone's planning on writing a research paper still, that as well. Did test marks change people's thoughts on doing a research paper, or do you still want to do those? Okay. Since next week is kind of screwy, plus I'm not even here on Tuesday, did I already give you kind of a day to do the research paper by? Did we say something with that? What was that?
The end of the week.
Okay. I won't mark them by then. Can we do it like the week after that Monday so you guys can have your long weekend to work on them? Does that work? And then I'll try to mark those right away because I'd like to get progress logs done for Thermochem and get them finished with. Yeah, basically, if you know that you need me to mark something that's late, make sure you work on that soon because I really don't want you to be focusing way too much on Thermochem when we start Electrochem. Because the first couple of days, I don't have any assignments for you to work on because like we need to learn stuff, right? So today, tomorrow, Monday, Tuesday, I can give you a worksheet to practice some stuff. But like, make sure you use these next couple of days if you're missing something late, get that done, okay? Okay. Okay, first unit was on thermochemical changes. So thermal refers to heat. Okay. Second unit's on electrochemical changes. Electro is going to refer to what? Yeah, electricity. Let's start by talking about that. Okay. What is electricity? Sure, that'll work. The flow of electrons is electricity. Okay, at the very least, you've all gone through grade 9 science at one point, I'm hoping. And in grade 9, I think you're supposed to learn about circuits to some degree. You learn about parallel circuits, and hopefully you kind of get the concept that, like, if you want to kind of rig up electricity, you maybe need a system that looks like this. Let's see. You might have, like, say, a battery. This is a battery here, perhaps. And then the battery is going to hook up to a light bulb, perhaps, or some sort of device. There's a light bulb. I'm a good artist.
Nice.
That's light. Will the light bulb turn on with this circuit set up like this? No, I think most of you intuitively know that, well, no, you need to have a fully functioning path. If that path gets broken, then the circuit stops, right? And what's really happening is, depending on which sides of the battery happen to be right here, the electrons are going around in a circle, like so. Does that make sense? And we're going to talk about this in chemistry, the direction of electron flow in a circuit. Some of you did physics with me last year. We did electron flow a bit in physics, did we not? Okay, so you might know like which way the electrons go based on negatives and positives. Typically, the idea is that electrons are going to go away from the negative end of the battery, if I have that right, because electrons are repelled by other negative things. So electrons will go this way. And then electrons will go towards the positive end of the battery because negative things are attracted to positive things. Does that make sense? And you might even have heard the words before, anode and cathode, the two different sides of a battery. So there's some knowledge that you might have before we start. Back to what I was getting at here, the concept of electro. We're going to talk about, from a chemistry point of view, how electrons move. Okay? And the logical end game in this unit is going to be talking about batteries. Because someone was really clever. They figured out that if in a chemical reaction electrons need to move, if we can try to find a way to make those electrons move along a wire, we can actually run our devices. Let me see if I can draw another picture here to illustrate what I'm getting at here. Here's a battery, for example, looks like this. Here's the, I don't know which one is which, positive and negative end of a battery, for example. Well, if the electrons went from this negative end of the battery to that positive end of the battery internally inside the battery, how effective would that be? It would be useless, because how are you going to run your devices? What you really need for them to do is separate this positive and negative, like have a boundary in between here, so that the electrons are forced to go like around the outside. Does that make sense? And if you can force them to go around the outside, there's a chemical reaction happening right here where substance A and substance B are coming into contact with each other, but we're actually forcing the electrons to go along a different path, if that makes sense. And if we can do that, then yeah, you hook up an iPod or a light bulb or something like that over here. I don't know, whatever the device is. Does that concept make sense? That's the worst iPad ever. Okay, so anyways, in terms of how this unit works, we're going to start talking about the theory behind, and today is mostly terminology based. We're going to learn a lot of words and definitions. As we move along, we're going to transition into equations and talk about some of the chemical equations that happened. And then the last half of the unit really focuses on batteries. We have a different name for them. We call them cells. And there's two different types. There's something called a voltaic cell and an electrolytic cell. You ever heard those words before? Oh, we have. Okay. For those of you who haven't, a voltaic cell basically describes a battery as it is operating. Okay? Imagine your cell phone, for example. If your cell phone's not being plugged in right now and it is using juice and it's running, it's currently using its battery as a voltaic cell, and it's using chemicals to provide energy. An electrolytic cell is the opposite. It's where you plug your iPod into the wall and it recharges. Does that make sense? That's electrolytic. And they kind of work in tandem. Basically, voltaic uses the energy, and then electrolytic recharges it. Voltaic uses, electrolytic recharges. And people who manage to figure out how to create batteries from chemicals, I mean, I have the utmost respect for them, because it's why we have devices such as our iPods, pacemakers, keep people alive. Your car actually functions like that, because your battery will recharge while you drive due to your alternator. Have you ever heard that before? Okay, I'm getting off topic. Let's get started. I do that a lot. Okay, first term I need you guys to know, it's the phrase redox. Okay. Redox is actually like an amalgamation of two words. It stands for reduction and oxidation. Let me go back to the battery concept. A battery has two different poles on it, the positive end and the negative end of the pole. Well, each of those two poles has a different chemical reaction taking place. One of them is considered to be a reduction equation, and one is considered to be an oxidation equation. If you have a positive and a negative end of a battery working in tandem, then it's called redox. Okay? Two equations occurring hand in hand. And hopefully this next sentence makes intuitive sense. If one substance is going to lose electrons, the other one has to gain electrons. Because this is all about electron flow. Back to this picture that I drew way back here. This end of the battery right here is losing electrons. Well, law of conservation of mass would dictate that you can't just lose an electron. It can't just all of a sudden vaporize. So where does that electron have to go? Well, it has to go around the circuit, all the way around through the light bulb, and show up over here on the other end of the battery, where that end of the battery has now gained the electrons. Does that make sense? So you always have to have these two things working in tandem. Someone's going to lose, someone's going to gain. And, I mean, hopefully this also makes sense here. The number of electrons gained better be the same as the number that's lost. You can't have someone gain 5 electrons, but the other end of the battery lose 7. Does that make sense? Okay. Like law of conservation of mass is basically the concept here. There actually is also a law of conservation of charge, by the way, which I think we did in physics as well. So, many reactions that you wouldn't think of as a redox reaction actually happen to be. If we can find a way to prove that electrons are moving, that's basically what defines something as being a redox reaction, if there's electron movement. So believe it or not, the three things, well, actually corrosion isn't one of the ones, but like we learned about photosynthesis last unit. We learned about cellular respiration last unit. Those are actually redox equations. We can actually separate them into something that's losing electrons and something that's gaining electrons. So I'll show you that as we get to equations there. If I kind of go back in history to like predating like the major booms of chemistry knowledge, I'm just trying to think of what you should know. Do you guys know let's work backwards in terms of famous chemists. Do you guys know who Niels Bohr was? Do you recognize that name? What was Niels Bohr's contribution to chemistry? The Bohr model of the atom, which basically states that electrons exist in different energy levels, different orbits. Bohr came around in about 1900, so around the time frame there. Working backwards, before the Bohr model of the atom, there was like the Rutherford model of the atom. You guys heard that before? Or the Dalton model of the atom, or the Thomson model of the atom. If we talk like even before that, it's probably only about 500 years ago that we can get to a point in history where chemists really had no clue what they were doing. Like they really did. They did not understand the concept of the periodic table yet, because Mendeleev hadn't actually put it together until like 18 something. Okay, so that's what I'm talking about right here. Like early men managed to figure out though how to do metals and ores, and they actually were doing electrochemistry without understanding what was happening. I don't know if I made that point clear enough. Chemists have really not understood the science behind electrochemistry until I would have to say like the last 200 years for them to actually understand what was happening. That being said, for hundreds, if not thousands of years beforehand, you guys ever heard of like alchemists? I talked about that before, maybe? Like, I mean, even crude scientists, they were actually able to do electrochemistry without understanding the concepts. I've actually seen a show where they managed to find a battery that Mythbusters were trying to make or create and try to replicate, where they found an ancient Egyptian battery that would be like 3,000 years old. You guys ever heard or seen things like that before? Where they found like these clay pots, and inside the clay pots, they managed to find some chemicals inside. Usually it's like lemon juice, things along those lines, and pieces of copper. And they found things that looked like prehistoric batteries that date back to like hundreds, if not thousands of years ago. The cool thing is that they understood how to do this, but they didn't understand what was happening. I like to think of like ancient magicians sometimes as being chemists. I watched a movie once before where they did a magic trick, and it's supposed to be set, in like the, I don't know, 1700s kind of thing. They did a magic trick where you have to lift the sword off of the ground. But the strongest person couldn't manage to lift the sword off of the ground. But then some guy comes along, the magician comes along and just lifts it right up. What did he do to keep the thing stuck in the ground? I used a magnet. But in order to get the magnet to work on command, it wasn't just a magnet, it was an electromagnet. Do you guys know what an electromagnet is?
It's basically a magnet with an on-off switch.
Yeah, it's a magnet with an on-off switch due to electricity, right? And so the magician understood the concept of how to rig this stuff up together, and they were able to recognize, hey, if I do this, this temporarily creates an electrical current that shocks me. And then if I use that in the right way, I can make a magnet turn on and off. But they didn't understand what was happening. They just were able to make it work. Does that make sense what I'm saying here? The idea that like our knowledge of the topic, we now understand the science behind it. But like we've known about how to make this sort of stuff work for a long time. And so where I want to start, I guess, is talking about extracting metals from ores. I got off topic again. I do that a lot. So this is actually the original definition of reducing things. Okay, if we're talking like a timeline here, maybe you've heard of like the Bronze Era, where like I don't even know that we should call them scientists, but where someone managed to figure out, hey, if we combine copper and tin, it makes a compound called bronze, and bronze is a lot lighter to work with, and so we can make our swords and shields out of bronze. Well, that was a bit of a chemistry thing where they had to try to find a way to take copper and tin and try to find a way to extract them from their ores. If I use the word ore, do you guys know what that means? Okay, so when we find, like, if you were to go to a mine, okay, you don't find pure metal typically in a mine. Okay, like say you were going to go to a mine and you wanted to find aluminum. Just going to write this down here. An aluminum mine does not give pure aluminum. What you're probably going to be mining is a compound like this, Al2O3. This is considered an ore. Okay. You're not mining pure aluminum, just like you're not mining pure, well, typically anything. Okay. The chemistry challenge now is, how do we take an aluminum ore of aluminum oxide, and how do we turn it into pure aluminum so that we can use that? Does that make sense? And that's where the chemistry came in, where ancient scientists, they didn't know the science behind what they were doing, but they understood that if they did this process, they could find a way to take aluminum and cause it to turn into aluminum solid and oxygen gas. taking an ore and refining it into a pure metal. That makes sense? And this is a process that's been around for, I mean, we can date it back thousands of years. The idea of taking an ore of copper, like say a copper oxide compound, or an ore of tin, like say SnO2. Finding that ore, that, you know, like the kind of a rock, but it's not pure, and finding a way to separate it into the pure metal. Okay? Well, the word they used to use to describe that then was called reduction. Okay? Reduction then became known as producing a metal from a compound. If you have an impure compound and you make a pure metal out of it, that was known as reduction. So let me give you some more examples. Here is an ore of iron, Fe2O3. Do you guys know what Fe2O3 is?
Rust.
It is. Actually, that's what I was going for. Yeah, it's rust, actually. Like when you've got flakes of rust on the side of a piece of metal, that's what this is right here. This is an ore of, basically, it's a rust. Okay? And if you were to add it to carbon monoxide, you could actually turn it back into pure iron. Cool. Right. This would be known as a reduction equation then, because you took an ore and made a pure metal out of it. Or here's a tin 4 oxide. If you attach it to some pure carbon, you could refine it. That's kind of a really good word to use here. Refine. If you refined a compound into a pure metal, that was reduction. Does that make sense? So again, ancient chemists, scientists, they were able to do this process. They just didn't know why it was working. Does that make sense? So, you know, they find a cool rock, and it happens to be a rock made of this compound here. And they're like, well, this is a cool rock. What can I do with it, right? And so then they, you know, grind it up maybe, and they try to melt it and try to turn it into a sword, but this doesn't take. Right? So then they experiment, and they find just some carbon, maybe left over after a fire, just some ash. And they combine the ash with this, you know, rock they have. And lo and behold, they manage to make pure tin. You know? And then they take that tin and they combine it with something else, and they make bronze. Do you guys get where I'm going with this? Okay. Okay, another word I need you to know then. The term then became known as a reducing agent. Okay? The reducing agent is the other thing that you use to cause a compound to turn into a metal. So one more time. The reducing agent is the thing that causes the compound to become pure metal. Do you guys think you could identify the reducing agents in the 3 equations above? Carbon monoxide would be the reducing agent because it helps this thing turn into that one. So then the carbon, like a carbon dust, and hydrogen gas. Those guys would be the reducing agents because they promote reduction in something else. I want to revisit a first concept I mentioned. Modern days, the best way for me to talk about electrochem is to use a battery. Remember, a battery has 2 poles. The positive and negative, the anions and the anode and the cathode. It has to have 2 different equations happening. This equation right here is actually 2 equations in one. There's an equation here where I'll even try to highlight them. I'm getting a little ahead of myself, but I think you're getting the concept. What's the highlighter? There it is. Where this iron is turning into this iron. That is 1 pole on a battery, if you will. This carbon monoxide is going to turn into this carbon dioxide. You see how they kind of come in pairs? Those pairs later on are going to turn into your positives and negatives, your anodes and cathodes. That makes sense? Okay, let me move on. I feel like I'm repeating myself a lot. Ancient scientists also understood an opposite process at the time, but they didn't actually know that it was the opposite until much, much, much later. But they understood the concept of taking something pure and having it turn into a compound. Probably the best example would be rusting. You have some pure iron, add it to oxygen, and it happens to turn into iron oxide. It goes from a metal into an ore. Okay. Hi.
Sorry, take that fish
Yeah, for sure. Just standing in the door over there. Here, take one of the back tables, maybe. Okay, sorry guys. Let me start again here. So opposite of reduction is oxidation. Okay. If reduction is taking a compound and making it pure, oxidation is taking a pure metal and converting it back into a compound. Does that make sense? Okay. The reason they called it oxidation is that almost all of the chemical formulas they were knowing at the time seemed to involve a commonality, the commonality being oxygen. You know, oxygen right here is the thing that turned something pure back into an ore. Does that make sense? And they recognized that it seemed to be from the air that was causing the problem. That makes sense? So hence the two names. Reducing an ore back to a pure metal and oxidizing a metal back into some sort of compound. It wasn't until years later that scientists actually had a better understanding of what was happening and were able to actually understand the intricacies involved. If electrochemistry is the study of electrons, it wouldn't have been until the discovery of the electron. Do you guys remember who discovered the electron? J.J. Thomson. You guys remember that name at all? Thomson did an experiment. Sorry if you haven't done physics. I'm going off topic, but you should know this stuff. J.J. Thomson did an experiment with something called cathode rays. Basically, he had this device where there was like a magnetic field put above a stream of particles, and the particles sometimes deflected up or deflected down based on some properties involving positives and negatives. And he was basically able to determine his model of the atom, which said that it was called the plum pudding model. You ever heard of that phrase before? Where he thought that an atom was made up of like a positively charged pudding, and that there were little negative raisins inside of it. And that was all within a positive pudding. You guys ever heard that before? Okay. Anyways, the point I'm trying to make here is that although people knew how to do chemistry, they didn't understand the what was happening or the why it was happening until we were able to learn about things like the nucleus, the electron. And so J.J. Thomson doesn't come around until like, I don't know, 18 something. So this is fairly recent in terms of chemists' knowledge of what's happening. Okay, moving on. Here are some more examples of oxidation reactions. However, you'll notice that only one of them involves oxygen. This one involves oxygen, so this is a good oxidation reaction. We took magnesium and made it from a pure metal into an ore. We actually did that reaction in our lab. Do you guys remember this? I took magnesium, I lit it on fire. It combined with oxygen in the air, and it turned into basically a white powder. That was a thermochemistry reaction, but it was also technically an electrochemistry reaction based on what we are later going to talk about in terms of electrochem. Okay. But oxidation was actually a poorly chosen word because the basic concept is that you want to take a metal and turn it into an ore. A metal turn into an ore. A metal turn into an ore. Oxygen could be the thing that promotes that. But it doesn't have to be oxygen. It could be chlorine. It could be bromine. So the word we use here is then oxidizing agent. That's the thing that promotes a metal to turn into a compound. So those are the words I need you guys to know. Starting from scratch then. I need you to know the word redox. Redox, I'm going to focus on more over the next little while, but redox refers to a reaction in which both reduction and oxidation takes place. Okay, it's just kind of a blanket term. So then that leads to the question, well, what is reduction? Historically, reduction was taking a compound and making it into a metal. In order to do that, you're going to need a reducing agent. The opposite of reduction, we've since learned, is going from a metal back to a compound. That's like rusting. Rusting is basically oxidation. In order to do oxidizing, you're going to need an oxidizing agent. Okay. Most of the time, they thought that oxygen was the oxidizing agent. It's not true. We've learned more about chemistry since we understand more, but those are the words I need you to know. So far, so good? Okay. Don't forget all of that, but since Thomson, I'll talk about why this is relevant. Okay. Since the discovery of the electron, since the discovery of the nucleus, since our modern day understanding of chemistry really exploded due to people like Niels Bohr, Ernest Rutherford, J.J. Thomson. Maybe you know some of these names. If not, I mean, you guys will do it in physics next year as well, okay? But because of like this revolution that happened, we now understand on an internal level more of what's happening. And so what we've now since discovered is that what's happening in an oxidation reaction is someone is losing electrons. And we've discovered that what's happening in a reduction reaction is someone is gaining electrons. And so most teachers in most places actually use this like mnemonic memory device called Leo the Lion Says Grr. I learned this when I was in high school. I'm sure we'll be teaching this in 50 years still. Just because it's an easy memorization device to help remember it. So if someone is going to lose electrons, it's oxidation, Leo. And if someone is going to gain electrons, it's reduction. Does that make sense? I want to go back to the slides that I did now, and I want to show you how someone is gaining or losing electrons. Let's go back to reduction. I'm just going to erase some of this stuff here. Okay, so this was called reduction. It was called reduction historically because an ore was being reduced into a metal. But now we know that there's a bit of a better definition behind it. According to Leo Says Grr, someone should be gaining electrons. Okay, let me see if I can prove that to you. By the way, this would have taken the discovery of charges. Again, you need to know about protons and neutrons and electrons to actually discover this fact. But what is the typical charge on, like, say, iron right here? What sort of charge would you assign an atom? Anybody know? What was that? What would the normal charge of an atom be? Why does an atom have no charge? Go back to like the first couple of weeks of chemistry, like even ever. What defines an atom versus an ion?
Electrons and protons.
Yes, electrons and protons. An atom should have equal electrons and equal protons, should it not? So therefore, if this right here, if you agree this is an iron atom, it should have no charge to it. Does that make sense? Ideally, if it's an atom. If it's an ion, ions have different numbers of protons and electrons. And if you look on your periodic table, we've now known about some of the different typical charges. You know, like iron could be +3 or +2, or calcium is +2. Does that make sense? But those are ions. Well, ions form together right here in this compound. What sort of charges would these guys have in the compound? Well, hopefully you remember this from like way back in the day, but oxygen usually has a -2 charge. So therefore it means that iron must have had a +3 charge. Does that make sense? Okay, well now let's talk about electrons. This iron right here would have had a +3. And then somehow +3 charge turned into 0. How do you go from a positive back down to 0? Well, there's two possibilities. To go from a positive back down to 0, you can either lose your positives. However, can you lose positives in chemistry? The reasoning is the protons are found in the nucleus and they don't move. So if you can't lose positives, what you could do is gain electrons, hence gaining electrons is reduction, Grr. Does that make sense? Now, again, ancient scientists, they were able to perform these reactions because they just messed around. Okay, I'll take that stuff Tuesday. You got my note? Yeah, I did. Okay. Ancient scientists were able to perform these reactions. They just didn't know what was happening at the time. But now we can look at these things and say, hey, look, there is a positive charge turning into a 0 charge. Someone must have gained electrons. Let's do some more reactions. Let's just find the commonalities here. What would the charge on this tin right here be? Well, 0, because it's an atom. What's the charge on this tin over here? Let's work backwards. Oxygen we now know is -2, but there's 2 of them, so that's -4. So this must be the positive 4 version of tin. If tin is going to go from a +4 to a 0, then how does it accomplish that? It does that by gaining electrons. Does that make sense? Now, the hard part is trying to find a way to keep this tin from coming into contact with this tin over here. If you can find a way, from a technological point of view, to have this tin and this tin cause the electrons not to go from here to here, but have the electrons go from here to there, and you put your iPad or your light bulb up there. Does that make sense? That's what makes a battery. Because as soon as we recognize that electrons are flowing from one tin to the other tin...
Breakfast?
Thanks. But if we can try to find a way to...
Skeleton.
If we can try to find a way to break that chain so that this tin and this tin, they don't transfer their electron directly, but they transfer them around a path, that's what creates our battery. Does that make sense? So, same thing here. This copper has no charge, because it's an atom. This copper right here has probably a +2 charge, so therefore copper is gaining electrons. Same concept. On this page right here, if someone is going to be gaining electrons, chances are someone should be losing electrons as well. So loss of electrons is oxidation. We now understand that actually in an oxidation reaction, someone is losing electrons. Let's try to prove that. What would the charge of this magnesium right here be? 0, because again, it is an atom, it appears, right? No charge. What is the charge of this magnesium over here, then? Probably +2, because the oxygen is -2, right? Well, how do you get from a 0 to a +2? How do you become more positive? You can't pick up extra protons, because if magnesium grabs more protons, it turns into aluminum or silicon. I'm just saying, here's magnesium. If magnesium gets more protons, it would become, that makes sense? So you can't gain more protons, so what you can do, though, is you can lose electrons. So we've since discovered that what people were calling oxidation, really what they were visualizing without even knowing it, is they were seeing compounds that were losing electrons. So, the mnemonic device one more time then. Whenever something is being oxidized, again, the name oxidation historically came from people recognizing that oxygen was combining with elements. Oxidation is actually something that is losing electrons. And reduction, historically, reduction was called that because things were reducing from an ore down to a pure metal. And that's why they called it reduction. But we now know that reduction things are actually gaining electrons. And they both have to go hand in hand, though. Because if someone is gaining electrons, somebody else better be losing them for it to happen. Does that make sense? Okay. I've also seen this mnemonic before, if that helps. If you don't like Leo says Gur, which is kind of the classic, you could use oil rig. I don't know. You need to memorize that concept, though. You have to know all these words. This is a very terminology-busy unit. You need to know all of these words. Okay, and they need to come to you fairly fluently. So like when I talk about oxidation, you have to know what I'm saying. Okay, so more definitions here then. We talked about that oxidizing agent. Okay. Where does an oxidizing agent occur? Okay, well an oxidizing agent occurs in an oxidizing equation. Boy, let's try this again. Let's go back here. These guys here are oxidizing agents, correct? Yeah. Okay, so these guys are oxidizing agents. Oxidizing agents promote oxidization, and hopefully you'd now agree that oxidizing means that someone is losing electrons. We just talked about that, right? Well, if this guy right here is losing electrons, where are those electrons going? The electrons are going to this guy. Does that make sense? So the oxidizing agent is actually the thing that takes the electrons. Let me say that one more time. Okay. Oxidization means someone is losing electrons. So we've already talked about how this guy right here is going to be losing electrons. Well, you can't just have somebody lose electrons. Someone else has to take those electrons. So the oxidizing agent is actually the one that takes the electrons. Does that make sense? Hopefully that's what I have written on the slide right here. An oxidizing agent now is actually someone that accepts electrons. What is that going to mean a reducing agent does? Yeah, the opposite. A reducing agent is someone that's going to donate or give electrons. Let's go back to my reducing agent slides and talk about that then. So here was a slide where we talked about reducing agents for the first time. So let's do this again. So hopefully we're all clear that these guys in this column right here, they are the reducing agents, which I'll just usually abbreviate with RA. Right here, this guy was going from +3 down to 0, so that guy was supposed to be GER, gaining electrons. Well, how is this guy right here going to be gaining electrons? Well, he's only going to be gaining electrons if he can take the electrons from somebody. Well, who is he going to take the electrons from? This guy right here. This guy is going to, like, donate the electrons so that this guy can gain them to turn into that. Say that one more time. This species right here, the reducing agent, is going to give away some electrons. In doing so, it's going to give the electrons to this iron right here. And then when the iron takes those electrons, it will then have gained electrons to turn into this guy right here. So new definitions and old definitions I need you to know. Okay. Old definitions are more historical. Sometimes you'll hear them as the operational definitions maybe, or the empirical definitions. Maybe you'll hear those words. The modern scientific definitions though are that reducing agents donate electrons. If you need to, write this down in your data booklet. But at some point you need to memorize all these terms. By the way, don't feel bad if you kind of need to walk through a process. Like for me, when I need to think of a reducing agent, I actually have to walk through and say, okay, Leo says GER. Okay, Leo says GER means that GER, gain of electrons, is reduction. Therefore, reduction means someone is gaining electrons. Therefore, that means the reducing agent must be the one giving the electrons. Like whenever I think, I literally have to go through that whole process every single time to think of this. So. Okay, let's talk about some equations now. Let's do an example here. Let's try to predict the products, the half reactions of oxidization and reduction in the following scenario here. We're going to take some zinc metal and we're going to place it into copper 2 sulfate. So very, very basic thing to start with. So what's zinc metal? What's its formula? Right, so Zn, let's go with solid. And let's put it in a solution of copper 2 sulfate. So copper 2 sulfate is going to be CuSO4. State of matter. State of matters matter, by the way. Like, it is very important. I'm kind of picky on that. Sometimes I forget, but you really should put down states of matter because it can make a big difference sometimes. For example, liquid water versus gas water on the previous table, on the thermochem table, there's a difference there. So, and there's differences in this next unit too. Everybody okay so far with how I started this? Okay, now, when I give you an equation like this, you can still use the chem skills you've learned before. What kind of reaction is it going to be? Okay, it's going to be a single replacement and, by the way, it's going to be redox. It's both, technically. But single replacement indicates that you're going to have zinc going with the sulfate. That's probably aqueous. And you're going to have copper by itself. Hazard a guess on state of matter for copper? Probably solid, yeah. Wait, and one of the things that I should have taught all of you at some point is the term spectator ion. You guys recall that term? There's a spectator ion in this equation. Who? Go ahead. Who's the spectator ion? SO4s, yeah. Why? Yeah, it's like it's on both sides here. Does that make sense? Now you might argue, hang on, Chris, there's zinc on both sides. That's not the same thing though, because this is solid zinc and this is aqueous zinc, and there's a difference. Again, states of matter matter. Okay. So if I wanted to kind of write this equation out, it would look like this. Zinc solid is going to take some copper 2 plus aqueous ions, turn into some zinc 2 plus aqueous ions, and turn into copper solid. There is our net equation. Hopefully up till now, that was review. Like, if I asked you to do that, you probably could do that without new information. The key now is I want to start using the definitions I've just taught you and try to talk about who's being oxidized, who's being reduced, who's the oxidizing agent, who's the reducing agent. So let's try that. According to the acronym or mnemonic or whatever it's called, LEO says GR. We need to try to figure out who is losing electrons and who's gaining electrons. So let's start with losing electrons. Here, there's kind of a pair, copper going from 2+ to copper solid. And here's another pair, zinc going from zinc to 2+. Which one is the one that's losing the electrons? Zinc is correct. Let's talk through that. Zinc starts with no charge and somehow goes from no charge to becoming 2+. Well, you can't become more positive by adding protons, so the only way that that can happen is that you lose electrons. So zinc must be losing its electrons. Does that make sense? Well, zinc can't just lose electrons without somebody else picking them up. So hopefully this works out well, that the copper pairing is going to gain some electrons. Here, copper starts at 2+ and goes to being something with like no charge. To go from a positive to a no charge means you'd have to pick up some negatives and gain some electrons. So now I should be able to talk about who's being oxidized and who's being reduced. I could say that, like I could write a statement. I could say zinc solid is oxidized. And I could write that copper 2+ is reduced. Does that make sense? We can even use the historical definitions to make sure this makes sense. Is copper being reduced? Well, look, what is copper turning into? Copper is turning into solid, pure copper. It was going from an ore or a compound of some kind into a pure metal. That's actually where the word reduction came from, turning something compound-wise into something pure. Does that make sense? So what was my question again here? We want to, okay, so we now need to do the oxidizing agents and the reducing agents. Okay. So if copper right here is being reduced, that means that this guy right here is the reducing agent. Because the zinc is the agent that causes copper to be reduced. Does that make sense? Vice versa, if zinc is being oxidized, this copper right here is the oxidizing agent. Because this guy right here is the thing that causes the zinc to be oxidized. On the diploma, they like to give you a lot of multiple choice kind of questions where they'll just ask you statements like, okay, well, who is the reducing agent? Who is the oxidizing agent? Who is oxidized? Who is reduced? And like it's different because the zinc is oxidized, but the copper 2+ is the oxidizing agent. And here, the copper 2+ is reduced, but it's the zinc which is the reducing agent. Does that make sense? Let me say that one more time. Zinc is oxidized. We know this because I can visually see that zinc is going from no electrons to 2 electrons. Sorry, no, going from no electrons to a positive 2 charge, which means it must have lost electrons. LEO is the acronym. So you lose electrons, this guy must have lost electrons. In order for him to have lost electrons, that is because this guy right here stole them. That makes sense? Vice versa. This guy right here went from here to there. It went from 2+ to 0, meaning that it gained some electrons. So how did this guy gain electrons and become reduced? Well, it's because it stole electrons from zinc. The zinc gave them away. Okay, last thing here, then we'll take a break because I've been talking for a while. How many more slides do I have? I have enough. Okay, we'll take a break after this. Okay, so one thing you might get asked to do then is to write something called half reactions. Okay. Again, we already know that the end game of this unit is going to be talking about a battery. Batteries have two reactions taking place. One is at the anode, the positive. One is at the cathode, the negative. I did that backwards, by the way. Sorry. Anodes and cathodes. So you guys know those words? You've heard those before? So what are the two half reactions? Well, one of the half reactions is this. Zinc solid turned into zinc 2+, and in doing so, it spit out 2 electrons. It lost electrons and became oxidized. So this is an oxidization half equation. So one more time. Zinc solid turned into zinc 2+. In doing so, it would have to spit out 2 electrons because it's losing electrons. Kind of like with thermochemistry. This is like an exothermic reaction in thermochemistry. There are electrons being written on this side of the equation. They are being lost. Actually, that's not true. They're not being lost. Someone else is taking them. Reduction means that someone else is taking them. Copper 2+ is going to take those electrons, and become copper solid. This guy right here is gaining electrons. These are called half reactions because these guys are really half. Sorry, give me a second to write here. These guys are called half reactions because hopefully you can visualize that these are the two halves of this equation right here. Does that make sense? This guy would be called the redox equation because there is reduction and oxidation happening. The halves are the zinc to the zinc and the copper to the copper. Using Hess's law, what cancels? The electrons. This guy loses electrons. This guy gains them. If we were to add these equations back together, we would get the one we started with. Does that make sense? Okay. Why don't you guys take a break? I know there's a lot. Sorry I'm going to be talking for the next couple of days. Am I doing okay so far? Do you guys think that makes sense? Okay. Take a break. We'll keep going after the break. Okay. I apologize that I'm repeating myself a lot today, but I really want to make sure that you have a solid foundation, because if you don't know the words that we're going to talk about this unit, it makes it really hard to communicate. So, quick recap from the top. If something is being reduced, you can look at it two ways. Reduction could be considered that an ore is turning into a clear metal. Or you could consider that reduction is something that is gaining electrons because of GER, gain of electrons reduction. That make sense? Oxidation, you could consider oxidation to be where you add oxygen or some other compound to a pure metal and cause it to rust and turn back into a compound. That was like the original thought behind oxidation. Nowadays, we recognize that oxidation involves the loss of electrons, hence the LEO concept. Okay? In order for oxidation to occur, an oxidizing agent has to be the other thing. And according to reduction to occur, a reducing agent has to be the other thing. Does that make sense? So going back to that again, reduction is the gain of electrons. Well, where is it going to gain electrons from? Well, gain of electrons is reduction. It's going to gain electrons from the reducing agent. So therefore, reducing agents give away electrons. In oxidization, oxidization means that someone is losing electrons. Where are they losing those electrons to? The oxidizing agent is the thing that takes electrons. Does that make sense? Okay, so with that recap done, let's just do a few more examples here then. So here's another example. Here, I don't know why there's an R in the middle. It's supposed to be an arrow. Such weird formatting. We're going to take some copper, add some silver nitrate, make it copper, nitrate, and silver.
Reaction.
Sure. Okay, right off the bat here, there's a problem with this equation, which hopefully you guys can see because I've taught you chemistry for a year and a half at least. What's wrong? Good, yeah, it's not balanced. Redox reactions, just like any reactions, need to be balanced. So we need to put a 2 here and a 2 here. I'm going to come back to that concept a little bit later. Hopefully there's a learning point here. Can you guys see who the spectator ion is in this example? Just kind of visually see it already?
Three.
Yeah, NO3, right? The NO3 is on both sides here. It's aqueous in both cases. So hopefully you can kind of start seeing the two different parts of this reaction. Written down below here, there's going to be some Ag positives turning into Ag solids. That's what I have written down here. Here's some Ag positives turning into Ag solids. Which side of the equation would electrons need to be written on to balance it? Well, if there's positives on this side, and that thing's supposed to be neutral, you're going to need to have a negative on this side so that a negative and a positive can balance each other to make it back to be neutral. Well, if an electron is written on this side right here, is it being gained or lost? Gained. This silver is gaining an electron. Gain of electrons is reduction. That makes sense. Once you start to get more fluent with these words, you'll then recognize that the thing that is being reduced is the oxidizing agent. Because they're kind of opposites of each other, aren't they? So once you figure out who is being reduced, it means that they are the oxidizing agent. And let's do the other one here. Here we've got some solid copper turning into copper ions. Solid copper into copper ions. Hopefully you'd agree then that the electrons have to be on this side of the equation. Because if this has a neutral charge, and this is +2, if I put a -2 over here, these two things will kind of cancel each other, equaling like a neutral reaction. That makes sense, like in terms of charge? So this must be losing electrons. So losing electrons is oxidization. Well, once you figure out who is being oxidized, the thing being oxidized is the reducing agent. Because they kind of work hand in hand. The thing that's oxidized loses electrons. In order for it to lose electrons, it must give away electrons to the reducing thing. Therefore, it's the reducing agent. So oxidized things are the reducing agents, and reduced things are the oxidizing agents. Does that make sense? Okay. One more thought here. These two equations right here, as written, they don't fit. Because this guy right here is going to try to gain 1 electron, and this guy right here is going to try to lose 2 electrons. This kind of even helps to explain balancing then. According to Hess's law, will this electron right here cancel with this electron right here? I'd say not yet. But if I double this, double this, double this, sure. Now they cancel. Does that make sense? Which goes back to the very first thing I pointed out, which was that this equation here wasn't balanced because you need to have 2 silvers to make it work. Now, going back to your thought process, why did you guys realize that you need to put 2s there? Was it the silver that tipped you off? I would think it was the nitrate that tipped you off, wasn't it? Because you looked at the 2 nitrates right here and got rid of those ones. And you say, okay, the nitrates were the problem, so therefore you put 2s in front of these. So one of the issues you may come across in this unit is, depending on whether or not spectator ions are written out, sometimes in order to balance, the only way to balance is to look at electrons and use that to help figuring out the balancing. Yeah, you guys can read. And you guys can read. Oh, I should point out a notation issue. Sometimes rather than putting a 2 in front of all 3 species, sometimes what we'll do instead is we'll just put a 2 in front of the very first thing, put a bracket around it. Think math, it's like expanding. The 2 just means that everybody gets a 2. Does that make sense? It might be a little bit faster. Okay, here's a picture maybe to help describe what we just saw there. Silver and copper. Silver is being reduced and therefore gaining electrons. Copper is being oxidized and losing electrons. Sure, I'll mark it in a second. Thanks, man. Visually, here's what's happening here. Here's some copper solid. And here are some aqueous ions. And what's going to happen is this copper right here is going to, let's see, it's going to lose an electron so that the silver can gain the electron. And this silver right here will pick up an electron transfer between these things, causing the silver now to become a solid silver and attach itself to the copper. But in the process, copper had to lose an electron. And in losing its electron, it no longer is solid anymore. And so this copper guy, I guess I did the arrow in the wrong spot. It looks like that one is the one that did the transfer here. Does that make sense? This copper right here spat out an electron, and in spitting out its electron, causes this guy to become solid and attach itself. Actually, it spits out 2 electrons, so the other electron must have been attached to this guy, so this guy can attach itself to the copper metal. But in doing so, now that this guy has lost its electrons, it's no longer able to stay with the rest of the solid stuff, because now it's an aqueous state instead. Does that make sense? Okay, let's try our last example. So I think this is my last one. So why don't I do this one with you guys still, though? Let's predict the products. Let's find the half reactions. Let's label oxidizing agents, reducing agents for the following scenario. We're going to take some zinc metal, react it with lead 2 nitrate. So start with the beginning. Zinc metal, Zn solid. It is going to react with lead 2 nitrate, so that's PbNO3 That's aqueous. Alright, so pretend that I'm your grade 10 science teacher again. What does this make? It'll make zinc with the nitrate. Make sure you fit it together properly though. Zinc's charge is 2, right? Now we know that because we kind of teach things out of order. Right? Because we just tell you what zinc's charge is back in grade 10. But maybe we can actually see how this is going to work with the electrons in a little bit. But since zinc has a 2+ charge, we need 2 of those there, right? And you'll get lead by itself. So that's all. So far, so good? All right. Now, a grade 11 skill. One of the first things I teach you in grade 11 is look for spectator ions. What's on both sides of the equation? The exact same. Good. So we can now start to write out the half equations. I'll do that first before I write the net equation. The half equations are going to be that zinc solid is going to need to turn into zinc, and this guy right here must have been a 2+. That's one of my half equations. The other half equation is that lead solid is being produced over here, and it's being produced because of this lead 2+ over here. Does that make sense how I kind of figured out the 2 pieces? Okay, well, there's a lack of electrons. There's an electron deficit written in these equations where we need to try to figure out which side to write the electrons on. Hopefully you guys can see we need 2 electrons, right? The question is which side? Well, the answer is we need 2 electrons on that side over here. Can you guys see why it's supposed to be on this side over here, not that side for this equation? Okay, well then this one right here is going to need the 2 electrons on this side. Do the electrons balance? Yeah, I mean, that's fantastic. You have 2 electrons here and 2 electrons here. So I don't even need to double or triple a reaction. I mean, I know I just wrote them. This is kind of silly. I just wrote them. But according to Hess's law, I can kind of cancel them. So my net equation is going to be zinc solid plus lead 2+ as an aqueous, turning into lead as a solid, and zinc as an aqueous. There's my net equation. Let's label stuff now. So I got 4 things I want you to do. I want to figure out which equation is the oxidation, which one's the reduction. And then I also want to figure out who the oxidizing agents and the reducing agents are. So let's look at this equation right here. Is this equation right here with zinc, is it oxidizing or reducing? Are we gaining electrons or losing electrons? Okay, Leo says Gur, so this guy is the oxidization equation. If you want to write it out here just at first, this guy is losing electrons. Well, by default, then this second one here better be the reduction equation, because this one right here is gaining the electrons. That makes sense? Okay, the thing that gains the electrons is the oxidizing agent. The thing that gains electrons is the oxidizing agent. The thing that loses electrons is the reducing agent. So now I've labeled everything the way I need to. This guy here is the reducing agent. He is going to cause lead to be reduced. Actually, I want to make sure everyone can watch this. I'll give you a second to write. You guys good? Okay. If this guy is the reducing agent, this is the thing that will cause that guy to be reduced. Traditionally, what did reduction mean? Well, it means turning it into a pure metal. And look, lead is getting turned into a pure metal. Good. That fits everything. Everything comes full circle. Right here is an oxidizing agent. An oxidizing agent is supposed to cause something to become oxidized. It's supposed to cause this guy to be oxidized. Okay, well, oxidation traditionally involved oxygen, but that actually was not really the best definition. A better way of putting oxidation is that oxidation takes a pure metal and turns it into a compound. Here is a pure metal. Is it being turned into a compound? Okay, technically it's not shown as a compound right here, but don't forget, there is a nitrate attached to it though. We just eliminated it because it's a spectator act. So does everything fit? Yeah, I hope so. Does that make sense? So that's kind of the first skill I need to be able to have. And I know it's tedious and maybe a little bit boring and repetitive, but I need you to be able to look at equations now and identify all these terms, because before we can move on to the more complicated stuff, you have to be fluent in the language. And today is basically a definitions day. That sound good? Okay, cool. One last thought here, and then I'll pack up for the day. That was my last slide, right? Okay. There is a table in our data booklet all about oxidizing and reducing. Can you guys find that table? Oh, I might not have enough. Ooh. Okay. Some really smart kid, years and years ago, it was Liam O'Connor actually, discovered that he was getting really sick of having to write on his table. If you have a book like Dakota's, it may already be pre-written on, because you're going to do a lot of work with this table over the next couple of days. So Liam was really bright. He said, why don't you put it on a transparency? And then every time you need to work with it, you can just wipe the transparency off to do it for the next question. Does that make sense? So I'm going to start keeping up transparencies, but I might run out. So tomorrow what we're going to do is we're going to talk about how this table works. No, Jamie. I owe you guys a case. So I'll try to figure out how to make this work. So tomorrow we're going to learn how to use that table in your data booklet, but I'd suggest hold on to these ones instead, and maybe try to obtain a wet or dry erase pen that you can use on a regular basis, because you're going to use this table a lot. Okay. As you can even see as you're looking at it, it is a table of half reactions where everything is being written in the same format. There's something you're starting with. It then adds electrons, it gains electrons, and it turns into usually something solid. And it's called the standard reduction table. Okay. Do you guys remember how in the previous unit there was a table all about formation? If we wanted to talk about decomposition, we would just flip the table around. Well, this table works the same way. It's called a reduction table. If we ever want to talk about oxidation, we're just going to flip some stuff around. That's it. Does that sound good? Okay, that's all I got. Sorry that I'm talking for about an hour. Tomorrow I'm probably going to talk most of class 2 again. Sorry. You guys can start packing up or working on, I don't know. I guess if you really want something to look at, there's a few pages in your textbook you could read. Okay, I'm done.